Hello, and welcome to the second video in this series on constant current circuits. The main topic of this video is Kirchhoff's current law, which describes how currents behave in the parts of the circuit where three or more wires join. The word current here is a noun and means an electric current. This law is known also as Kirchhoff's first law. We will use the word node to refer to a point where three or more wires join. This example shows a node where 5 wires join. If these wires carry electric currents, then such a current generally can flow either away from the node or into the node. As we will see next, these directional differences will be accounted for in Kirchhoff's current law by using positive and negative signs. Having now defined what a node is, we have the language to state one of the two laws of electric circuits named after Gustav Kirchhoff. Following the sacred tradition of the exact sciences, we confirm, yes, Kirchhoff's last name really does have two H's in it. Kirchhoff's current law concerns the totality of all the currents that are entering or exiting the given node, each by its own wire. The law asserts, essentially, that a node cannot create new current, cannot destroy existing current, and cannot store electric charge. In a little more detail, at every instant in time, the total amount of the current entering the node equals the total amount of the current exiting the node. For a number of reasons, however, it is often more convenient to write this law in a form that has 0 on one side. Thus, on the other side, we end up adding all the currents, but taking each current with a positive or negative sign, depending on whether it exits or enters the node. Such a sum of signed terms is called an algebraic sum. Therefore, Kirchhoff's current law, often abbreviated KCL, states that the algebraic sum of the currents at a node equals 0. In physical terms, this is a current conservation law at a node. Two circuit elements are said to be connected in parallel if one node is directly connected to one terminal of each element and another node to the other two terminals of the two elements. We recall that a node is a juncture of 3 wires or more. Therefore, two circuit elements in parallel can also look like this. We are given two resistors connected in parallel. Their resistances are denoted R1 and R2. One pair of the shared terminals is shown as node A, the other pair as node B. Current I, flowing in the reference direction shown by the arrow, enters node A and splits up into currents I1 and I2, flowing through resistors R1 and R2, respectively. The question we explore here is whether the two resistors connected in parallel can be replaced by one resistor so as to produce the same current voltage characteristic between nodes A and B. By Kirchhoff's current law applied to node A, current I equals the sum of the currents I1 and I2. The same holds at node B. If now VAB is the voltage between these nodes, in the reference direction shown by the arrows, then Ohm's law allows us to calculate each of the currents I1 and I2. Adding the expressions for the two currents, and using Kirchhoff's current law, we are able to express current I in terms of voltage VAB and the two resistances R1 and R2. Now applying Ohm's law to the proposed replacement, we obtain an expression for I in terms of voltage VAB and resistance R. Comparing the last two equations, we see how to relate the two parallel resistances and their proposed one replacement. By solving the last problem, we arrived at the equation shown. This equation involves the reciprocal of the resistance, which is called conductivity. Using this term, we can state our finding for now as follows. Two or more resistors connected in parallel result in a conductivity equal to the sum of their individual conductivities. We have not yet explicitly proved the or more part. We do this in a later slide, after going over an example of a problem. In the circuit shown in the top left corner of the slide, the voltage V between nodes A and B and the resistances R1 and R2 are given. Compute the current I. You can pause here if you would like to examine the solution shown. We now present the promised proof of the frame statement that tells how to replace any number of resistors in parallel by one equivalent resistor. Let n resistors be connected between nodes A and B as shown. We now present the proof of the frame statement without commentary. You can pause here if you would like more time to examine the proof. Here is a problem that we will solve using what we have just learned about resistors connected in parallel. We are asked to find the current through resistor 4. We solve this problem by first simplifying the schematic, by making equivalent replacements, using what we have learned. First, we deal with the 3 resistors connected in parallel. Converting their resistances to conductivities, we replace these 3 resistors by 1. Having found the conductivity of this replacement resistor, we convert that conductivity to resistance. The result is shown in the bottom left corner of the slide. We now have 2 resistors connected in series. We combine them into one, using the results of video 1 on constant currents. The desired current entering terminal B in the reference direction shown is the same as it would be for the original schematic. Therefore, It is the current that flows through resistor 4. We find this current, denoted here by I4, using Ohm's law. It equals 1.67 amperes. This problem is a follow-up on the previous one. We are given the same original schematic, but now have to find the currents through all the resistors. As before, the three resistors in parallel share a terminal on the left-hand side. This terminal is denoted by the letter lowercase a. The other shared terminal of these three resistors will be denoted by lowercase c. Currents I1, I2, and I3 flow through resistors R1, R2, and R3, respectively. We show the solution without commentary, building on our results from the previous example. You can pause here if you would like more time to examine it.